All right, so I am recording this and I will post this onto Blackboard later this afternoon. All right, so we've been talking so far in chapter 3 about finding zeros of polynomial functions. And this morning, we're going to segue into some differing topics. And we're going to talk about rational functions in section 3.5. And a rational function is simply a ratio of two polynomial functions. So we'll talk about them in depth. And then we'll start looking at rational inequalities and polynomial inequalities. And we're going to solve inequalities using test points. So there isn't any graphing, although you could graph these if you wanted to. I highly encourage you to graph everything that you're doing in this chapter. So these rational functions you can graph, and the polynomial inequalities you can actually graph. But we'll do those using test values, okay? So what we're going to do in section 3.5 is, first of all, do a quick review of domains. So we've been talking about domains quite a bit since chapter 2. And since we're talking about rational functions, so we're going to take a polynomial and put it in the numerator and denominator, then there is a chance that your domain could be restricted from the set of all real numbers. So that's where we start with the assumption that the domain is all real numbers, and then we look for two restrictions, one of which is the square root of an odd, a negative number, and the other is when we have x's in the denominator of a fraction. And straight from that discussion leads us into asymptotes. We'll first talk about vertical asymptotes, and then we'll talk about horizontal asymptotes. And the method to find those two different types of asymptotes are completely different. And they mean something completely different. So we'll look at the techniques for doing that. And then we'll talk about transformations, just like in chapter 2, where you could take one of those standard 7 functions and transform it by moving it in the coordinate plane and reflecting it about the x-axis and stretching it or shrinking it. You can do the same thing to a rational function. And then we'll graph one, and then we'll talk about slant asymptotes. Okay, so what is a rational function? Rational functions are quotients of polynomial functions. This means that rational functions can be expressed as some function f of x is a ratio of two polynomial functions. So p and q are both polynomials. The domain of a rational function is the set of all real numbers except the x values that would make your denominator 0. So just like we've been looking at since chapter 2, when you're given a function like this, you need to look at the denominator and determine what values you need to restrict from your denominator so that you don't divide by 0. For example, here is a rational function. It's a rational function because its numerator is a function and its denominator is a function, polynomial function specifically. Okay, looking at this polynomial function, I can immediately see that there is a value of x that I must restrict. X can't equal 5. And I can determine that by setting the denominator equal to 0. So set your denominator equal to 0. And that will give you the restrictions on your domain. So x minus 5 is equal to 0. Add 5 to both sides. X equals 5. So 5 is the value that if I plug it into that denominator, I divide by 0. I can't divide by 0. So in set builder notation, we say that the domain is the set of all x's such that x cannot equal 5. It can be anything else, but it cannot be 5. And in interval notation, that's every number except 5. So you're going to have a hole in your graph at the number 5, but x can be anything else. So what's that? Is that from negative infinity to 5, union with from 5 to infinity? So everything except the number 5. I think I have everybody. Okay, thank you for putting your name in chat. I appreciate that. Okay, so how about this one? Well, again, we're going to set the denominator equal to 0. And in this case, when we set the denominator equal to 0, we have a quadratic equation. And you can do this a couple of 3 different ways. You can certainly solve that by adding the 25 to both sides and taking the square root. Or you could use the quadratic formula if you were so inclined. It's probably overkill for this particular problem. But I'm going to factor it. And I need to practice my factoring because when I talk about vertical asymptotes here in a minute, I need to be able to factor the numerator and denominator of this rational function to find vertical asymptotes. So I'm going to factor that. That is the difference of 2 squares. So it's going to factor to a sum times a difference. X plus 5 times x minus 5 is x squared minus 25. Set each factor equal to 0. So in set builder notation, x can be anything but, it can't be negative 5 or positive 5. So the set of all x such that x cannot equal negative 5, x cannot equal positive 5. Or in interval notation, we would have holes at both negative 5 and positive 5. So that would be from negative infinity to negative 5. In between negative 5 and 5, and from 5 to infinity. Anything but negative 5 or 5. Okay, how about this one? Well, in this one, there is no real number that would cause that denominator to be 0. If we set the denominator equal to 0, that is not factorable over real numbers. The solution to that equation is imaginary. As a matter of fact, complex conjugate solutions. So x would be plus or minus 5i. So since the solution to that equation is complex, then the domain is the set of all real numbers. There is no real number that if I plug it in for x, I get 0 for the denominator. Okay, so our discussion of finding domains of rational functions leads us to a discussion of what a vertical asymptote is. So what is a vertical asymptote? A vertical asymptote is a vertical line, and it has the equation x equals a constant. And it's a vertical asymptote if, as my function approaches that vertical line, it increases or decreases, which is the next slide, without bound. So if you look at the graph on the left here, as x comes from the positive direction. So it's coming from right to left. As it's coming from right to left, as it approaches that line, it increases without bound. It can't cross that line. It can't touch that line. It skims that line. That line is like a brick wall, and your function's like a fly. It can't fly through the brick wall, so it has to do something. So it comes up and it skims along the wall. So the first graph is as x approaches from the positive direction, this vertical line, it increases without bound. The second graph, the graph on the right there, is the same idea, but now x is approaching from the negative direction. So it's approaching that line from left to right. As it approaches that line, it can't cross it, it can't touch it, so it comes up and skims it and increases without bound. So a vertical asymptote is a vertical line, x equals a constant, such that your graph cannot cross or touch it. It will increase or decrease without bound as it approaches that line. So the next images are it's decreasing without bound. Again, it's a vertical line that your function approaches either from the right or the left. As it approaches that line, it decreases without bound. So vertical asymptote, vertical line, that is your graph of your function approaches that vertical line, it either increases or decreases without bound. So how do you find those? Well, to find a vertical asymptote, you look at the function. And what you do is you reduce it to lowest terms. So if there are any common factors in the numerator and denominator of your rational function, you're going to cancel those out. Then you're going to look at the resulting reduced fraction. You're going to set the denominator equal to 0, and that will give you a vertical asymptote. So if f of x is p of x over q of x, p of x and q of x are polynomial functions, and p of x and q of x have no common factors, and a is a 0 of the denominator, then x equals a is a vertical asymptote of the graph of the function f. So to find vertical asymptotes, you factor a numerator and denominator, cancel any common factors, set the denominator equal to 0, and that will give you a vertical asymptote. Because when the denominator is equal to 0, you can't have that. So in a rational function, that's one of two things. It's either a vertical asymptote or it's a hole in the graph. And we'll talk about that in a minute. Okay, so what are the vertical asymptotes of this function? And yes, it does have two vertical asymptotes. So to find the vertical asymptotes, I need to factor that denominator because I have to ensure that there are no common factors in the numerator and the denominator. There's not going to be, x is not going to cancel with a binomial factor in the denominator. So you're going to be okay there. But you do need to practice and get used to factoring numerator and denominator completely. So I'm going to factor this. The denominator is the difference of two squares. X squared is a perfect square, 1 is a perfect square. So the difference of two squares factors to the sum times the difference of the two square roots. There are no common factors in the numerator and the denominator. There is no factor of x plus 1 or x minus 1 in your numerator. So there's nothing you can cancel here. So now you set your denominator equal to 0. Set each factor equal to 0. Solve the resulting linear equations. And we get x is -1 and x is +1. So this function has two vertical asymptotes. at -1 and +1. So the vertical line x equals -1 is a vertical asymptote, and the vertical line x equals +1 is a vertical asymptote. So if you were to take your calculator out and you were to graph this, you're going to see this behavior of where the function's either increasing or decreasing without bound as it approaches these vertical lines from the left and or from the right. So here is the graph right here. And I encourage you again to take your calculators out. You purchased, borrowed, however you got one, you've got one. So you might as well utilize it as much as possible. So again, our two vertical asymptotes were -1 and at +1, and you can see this behavior. So looking at this graph, let's just look at it from left to right. So from left to right, the graph is approaching the vertical line x equals -1. It cannot cross that line, can't touch it. So at that, for this particular graph, it approaches that line x equals -1 and it decreases without bound. However, it has behavior between the two asymptotes also. So in between the vertical asymptote at -1 and the vertical asymptote at +1, it has this behavior where on the left side, it increases without bound, and on the right side, it decreases without bound. So in between those two asymptotes, as we approach from the right to the left, from right to left, the function increases without bound. As we look at it from left to right, as it approaches the vertical asymptote at 1, it decreases without bound. And then on the right-hand side of the asymptote at x equals 1, the function approaches from right to left for the positive side, and it approaches that vertical asymptote and it increases without bound. So you got all the behaviors here in this particular graph. It decreases without bound in a couple of places and increases without bound in a couple of places. All right. Okay, and this particular function doesn't have vertical asymptotes because the function, the denominator, there is no real number that will satisfy that equation. The denominator is not factorable over real numbers. So if I set it equal to 0, this equation only has imaginary solutions. So there is no x that would make that equal to 0. So no vertical asymptotes. And when you graph it, you can see this. This particular function, as you can see, has a domain of all real numbers. It is increasing in the x direction without bound to the right and decreasing without bound in the x direction on the left. So its domain is the set of all real numbers. There's no vertical asymptote. Okay, now let's look at this function. You've got homework problems like this, and as a matter of fact, a problem just like this will show up on your third exam. So find the vertical asymptotes of this function. And again, you must factor your functions, numerator and denominator, and cancel any common factors to find the asymptotes. So if we factor this, the denominator is the difference of two squares. X squared is a perfect square, 4 is a perfect square. So it factors to a sum times a difference of those two square roots. So it'd be x plus 2, x minus 2. So I can see from this that an x minus 2 factor will cancel. So this x minus 2 will cancel, this x minus 2 will cancel. So what you're left with when you do that cancellation is 1 over x plus 2. So setting the denominator equal to 0, I get a vertical asymptote at -2. So there is an asymptote at the vertical line, x equals -2. But what you canceled there, x can't be 2. If x is equal to 2, your denominator is equal to 0. If x is equal to 2, you're canceling a factor of 0 over 0. You can't do that. So the fact of the matter is there's an asymptote at x equals -2, but x cannot equal +2 either. That is a hole in your graph. So x cannot equal 2. It can't. This is a hole. Now, when you graph this on your calculator, you're not going to be able to see this. Now, the asymptote you can probably figure out. You can see the behavior of the graph as it approaches this vertical line, x equals -2. But the hole's not going to be real obvious because your calculator doesn't do a real good job graphing holes. But if you graph this on Desmos, and you can't use that on a test, but it's not bad to practice some of this to see the hole. And I did that. I graphed this on Desmos, which is probably kind of hard for you to see on your screens. Maybe your screens are big enough. But you can see, look at this behavior at x equals -2. As the function approaches that vertical line from the negative direction, it decreases without bound. It comes up to that line and it decreases without bound. As it comes from the right-hand side, from the positive side, as it approaches that line, it increases without bound. So there is definitely a vertical asymptote at -2. But as I was using my mouse scrolling over the right-hand side of this graph, I could see that at +2, this function is undefined. So there is literally a hole in your graph, a discontinuity at +2. It comes down here and it hops over +2 and then continues in the x direction. So there's a vertical asymptote at where your denominator is equal to 0. There's a hole when you set the factor that you cancel equal to 0. So since I canceled the x -2, if I set that equal to 0, I get x cannot equal +2. All right. What's a horizontal asymptote? Well, it's a completely different animal. So a horizontal asymptote is a y value that your function approaches as x increases without bound. So as we increase in the x direction without bound, there is a y value that your function's value actually approaches. So the graph here on the left, as we come from the negative infinity direction, the function's y value, its output, approaches this value b. Second, for the graph in the center, as we come from the negative x direction, our function's coming down and it's approaching this value for y. And then in the third graph, this illustrates the fact that horizontal asymptotes can be crossed. They can be touched. So it's purely a value that your function approaches as x increases without bound. Okay? So how do you find those? Well, you have rules. Oops, went too far. And these rules are in your notes for chapter 3. So there's no need to memorize these rules. They're given to you. Okay, so how do you determine horizontal asymptotes? And if you've taken calculus or you're going to take calculus, you're going to study limit theory. And this makes sense if you think about limit theory. As a matter of fact, my calculus student right now is doing horizontal asymptotes. That's what he's doing right now. So let f be a rational function given by the numerator and the denominator are polynomial functions. The degree of my numerator polynomial function is n. So whatever the largest exponent is in my numerator, that's the degree of my numerator. The degree of my denominator, we're going to call that m. So numerator is n, denominator is m. So whatever the degree, largest exponent in my denominator polynomial, that is the degree of my denominator. And then we compare the values of these two degrees. So if the numerator degree is less than the denominator degree, so n is less than m, then the x-axis is a horizontal asymptote. So the line y equals 0 is the horizontal asymptote. And I'm going to show you in a function in just a second why this makes sense. Now, if the two degrees are equal, so the numerator degree and the denominator degree are the same, n equals m, then the horizontal line that is created by a ratio of the leading coefficients is your horizontal asymptote. So if the degrees are the same, the horizontal asymptote is a line y equals a sub n over b sub m. And then if the numerator degree is greater than the denominator degree, there is no horizontal asymptote. Okay, so for example, here's my rational function, f of x equals 9x squared over 3x squared plus 1. So if we look strictly at the numerator, the largest exponent on any one of my terms, I only have one, the largest exponent up there is 2. So the degree of the numerator is 2. So n equals 2. If we look at the denominator, the degree of the denominator, the exponent in the denominator is also 2. So m is equal to 2. So it looks like that n equals m. The two degrees are the same. So if we go back to our rules for horizontal asymptotes, number 2 applies. If n equals m, then the line y equals a ratio of the leading coefficients is the horizontal asymptote. So our horizontal asymptote is going to be y equals a sub n over b sub m. And if my two functions in the numerator and denominator are written in descending order, then this is the ratio of their leading coefficients, or 9 over 3. And 9 over 3 is equal to 3. So y equals 3 is this function's horizontal asymptote. So why does this make sense? Okay, so a horizontal asymptote is a y value that your function approaches as x increases without bound. So just bear with me for a second here. Let's say x is increasing without bound. So it's going toward infinity. It's going to the right as far as it can possibly go. It's doing the same down here. So if we do that, that little plus 1, who cares? So let's say x is 1,000,000, for example. So you've got 9 times 1,000,000 squared divided by 3 times 1,000,000 squared plus 1. The 1 is absolutely negligible. The ratio of 9 times 1,000,000 squared divided by 3 times 1,000,000 squared plus 1 is approximately 3. So as x gets larger and larger and larger, that poor little plus 1 is completely and totally negligible. So the value of this function approaches the value of 3 as x gets larger and larger and larger. Right, and there is the graph of this, and you can see that as x goes to infinity, the graph of this function approaches the line y equals 3. Okay, how about this one? We have g of x is 9x over 3x squared. So the numerator is the polynomial 9x. There is an understood 1 on that x. So the degree of the numerator is 1. The denominator is a quadratic function, so its degree is 2. And if we go back and look at our rules, in this case, the numerator's degree is less than the denominator's degree, because 1 is less than 2. If the numerator's degree is less than the denominator's degree, then the x-axis, or y equals 0, is my horizontal asymptote. And again, this kind of sort of makes sense, because if you look at this function, what's the behavior of this function as x increases without bound? Well, both the numerator and denominator increase without bound as x increases without bound, but the denominator increases faster because of the x squared in there. So as x increases without bound to the right, the denominator gets larger and larger and larger faster than the numerator does. So eventually the denominator gets so large that the function approaches the value of 0. And that's what happens as denominators get bigger and bigger and bigger. You know, if you look at like a 10th or a 100th or a 1,000th or a 10,000th or 100,000th, as the denominator gets larger and larger and larger, that fraction approaches 0. It gets closer and closer to the number 0. So that's what this function does. As x increases without bound, this function's value approaches 0. And if you graphed it, you could see that. And there is the graph of it. So as x increases without bound, this function comes up and then it comes back down and it approaches the x-axis. And then how about this one? Well, if we look at the polynomial in the numerator, it's 9x to the third, so its degree is 3. If we look at the polynomial in the denominator, its degree is 2. If the numerator's degree is greater than the denominator's degree, which it is, there is no horizontal asymptote. And if I graph this, you'll be able to see this. Well, there it is. There is no y value that my function approaches as x increases without bound. Okay, so here, just like in chapter 2, section 5, we got our 7 basic functions. There are 2 basic reciprocal functions. The first one is 1 over x. The second is 1 over x squared. 1 over x is an odd function because it is symmetric with respect to the origin. If I input 1, I output 1. However, if I input -1, I output -1. It does have a vertical asymptote at x equals 0. The denominator cannot equal 0. It also has a horizontal asymptote at y equals 0. The degree of the numerator of this function is 0. There is kind of an understood x to the 0 in that numerator. X to the 0 is equal to 1. So the numerator degree is less than the denominator degree. So the x-axis is a horizontal asymptote. F of x equals 1 over x squared is even because it's symmetric with respect to the y-axis. It also has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0, because the numerator degree again is less than the denominator degree, This is x to the 0 over x squared. 0 is less than 2. So you can take these two basic reciprocal functions and transform them just like you did in chapter 2, section 5. You can translate them by moving them horizontally. You can translate them by moving them vertically. And you can even reflect them by multiplying by a negative. So for example, the function f of x equals 1 over x, you can see the graph there. It's the standard reciprocal function. Well, what happens if I add 2 to the x and then subtract 1? Well, if I add a constant to my input x, as you recall, that is a horizontal translation. And if I add a value to the x, that is a translation to the left. So we're going to take this standard rational function and we're going to move it to the left 2 units. The -1 outside that is a vertical translation. So we're going to move this function down 1. So we're going to take this standard rational function and we're going to move it 2 units to the left and 1 unit down. And it moves everything, including the asymptotes. So if you move this function 2 units to the left, that vertical asymptote at x equals 0 gets moved to x equals -2. And that should make sense to you looking at the function. You can say that x can't equal -2. Can't do that. So it moves the vertical asymptote to -2. It also moves the horizontal asymptote to -1. And that should also make sense to you, because what happens as x increases without bound? As x increases without bound, the denominator of that fraction increases without bound. And 1 over a really big number is about 0. It's approximately 0. So this function approaches a value of -1 as x goes to infinity. So not only do our vertical asymptotes get moved when we transform this, but our horizontal asymptote also gets moved as we transform this. So you can now see what the function looks like. It's graphed there in red. Okay. So in your homework, there are problems that you're going to graph rational functions. And it's pretty much a step-by-step process, everything that we've already done. So none of this is new, except maybe the asymptotes. So it's the same strategy we've used for graphing functions since chapter 2. Now, I also highly encourage you to take your calculator out and look at the graph on your calculator also, but you're going to have to find all this information. Whoops, that's not good. And plug it into your calculator. Plug it into MyMathLab. So the first thing you do is check for symmetry. And I don't know that any of these have any symmetry, but how do you check for symmetry? You plug in -x and see what you get. If you get the opposite of what you began with, it's origin symmetry. If you get exactly what you started with, it's y-axis symmetry. I'm pretty sure, if I remember correctly, none of these are symmetric, but I won't swear to it. So you need to test for symmetry. Then you find the y-intercept by evaluating the function at 0. You find the x-intercepts by setting the numerator equal to 0. The denominator cannot equal 0, but the numerator can. So if you set the numerator equal to 0, that will give you the x-intercepts, if there are any. And then you find the vertical asymptotes by reducing the function to its simplest form. So cancel any common factors if you have them, and then setting the denominator equal to 0. Find the horizontal asymptote using the rules that we gave you. Then plot at least one point and graph the function. Okay, so let's graph this function. The first thing that we need to do is test for symmetry. So to test for symmetry, we're going to evaluate the function at negative x. So where there's an x, we're going to replace it with a negative x. And what do we get? And I could, I suppose, if I wanted to, factor out a negative. Okay, is that the function that I started with? No. Is it exactly the opposite of the function I started with? No. If it were the opposite, it would look like this. So it is not the same. It is not the opposite. So there is no symmetry. So it's not symmetric with respect to the y-axis. It's not symmetric with respect to the origin. You can graph this and see this. So if you don't want to do the plug and chug, graph it and look at it to determine if it has any symmetry. Okay, find the y-intercept by evaluating the function at 0. So our function was f of x equals 3x minus 3 over x minus 2. So we're going to evaluate this at 0. So that's negative 3 over negative 2, which is 3/2. So it crosses the y-axis at 1.5. To find the x-intercepts, you're going to set the numerator equal to 0. So it does look like it has an x-intercept at 1. So it has a y-intercept at 3/2 and an x-intercept at 1. Okay, so now you're going to find the vertical asymptote if it has one. And it does have a vertical asymptote. I am going to factor this just to make sure there's nothing to cancel. So I'm going to factor a 3 from that numerator. X minus 1 cannot cancel with x minus 2. So set the denominator equal to 0. So there is a vertical asymptote at 2, x equals 2. To find the horizontal asymptote, look at the degree of the numerator and the degree of the denominator. The numerator is a first degree polynomial function, as is the denominator. If the degrees are the same, then the line y equals the ratio of the leading coefficients is the horizontal asymptote. So y equals 3/1. My leading coefficient in the numerator is a 3, and in the denominator, there's that understood 1 there. So the ratio of 3/1 or 3 is my horizontal asymptote. Okay. So then you plot all those points. You will not actually be plotting points in MyMathLab. You're going to, at this point, be given a choice of graphs, and you're going to pick the graph that looks like what you have. I highly recommend that you graph these on your calculator and match the window to the window that they give you in MyMathLab. So if their window goes from -20 to +20, -20 to +20, make your window the same thing. If their window goes from -5 to +5, match their window. Okay, so we graph the x-intercept at 1, we graph the y-intercept at 3/2, we graph the vertical asymptote at x equals 2. And then they recommend that you find points. Now, if you've graphed these, if you've graphed this function, your calculator can find these values for you. So all you have to do on your calculator is go to your calc menu, which is above your trace. And number one is value. So if I inputted this function into my calculator, I can find the y value for the given x value. Let's just do a quick demonstration of that. I've got a little bit of time here. So I'm going to go over and open my calculator, and I'm going to graph this function. Okay, so I'm going to graph this using my fraction button, which I can find by doing alpha y equals. So if I hit the alpha key and y equals, number one is my fraction. So I'm going to type in the 3x minus 3 in the numerator, and then I'm going to arrow down to my denominator and x minus 2. Okay, oops, I forgot my x, didn't I? Go back over there and get my x in there. There we go, x minus 2. All right, so I'm going to do a zoom standard because that's where I always start if I haven't graphed in a while. And you can see the behavior that I was talking about. You can see that at +2, this thing is decreasing without bound as it comes from the negative direction and increasing without bound as it comes from the positive. Okay, and you can see that it's crossing at x equals 1, and it looks like it's crossing the y-axis at 1.5. Okay, so let's say I want to find these values. Let's say I want to find what what y equals when x is -1. So I go to my calc menu, which is above the trace. So it's right there above the trace. So I go second, calc. Number one is value. I want to know the y value when x is -1. So I type in -1 and enter. So when x is -1, y is 2. Type that into MyMathLab. They wanted you to find it like at -1/2. So go second, calc, value, 1 divided by 2. And it's 1. So all these values in this table you can find using your calculator. Now you can also plug them in to the function and find the value. It's just kind of easier at this point in your career to use your calculator. All right, let's go back to the PowerPoint. So I have found these values. There they are in the table. And then I'm going to graph the function. So I'm going to pick the graph out that looks the most like this. We've got an asymptote at 2, an asymptote at 3, it goes through the y-axis at 1.5. It goes to the x-axis at 1. So it does something like this. And then it's got to do something up there too. So you might plot some points up there if you were plotting this by hand. But since it has this behavior to the left of the vertical asymptote and below the horizontal asymptote, it's got to have the same kind of behavior above and to the right. So it's going to increase without bound as it approaches the vertical asymptote, and it's going to approach the value of y equals 3 as x increases without bound. Okay, our last topic is slant asymptotes. And slant asymptotes occur in general. Well, if you have a particular value for the numerator and denominator degree. So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. In general, if f of x equals p of x over q of x, p and q have no common factors, and the degree of p is 1 greater than the degree of q, find the slant asymptote by division. So what you do to find your slant asymptote is you use division to divide your numerator by your denominator. And you know how to do this. You can either use long division or synthetic division if it's appropriate. If your denominator is linear, use synthetic division. If it's linear and its leading coefficient is 1, then use synthetic division. Okay, so does this function have a slant asymptote? And the answer is yes, it does. It has a slant asymptote because the numerator's degree is 2. The denominator's degree is 1. 2 is 1 more than 1. So since the numerator degree is 1 more than the denominator degree, then we can use division to find the slant asymptote. So what I'm going to do, and I'm going to use synthetic division. I'm going to use a divisor of 2, and I'm going to divide that numerator. And I only need, I don't need the remainder. I only need the first couple of terms here. So I'm going to bring the 2 straight down. 2 times 2 is 4. That's 1 minus 2. And I don't really care. I don't care about the remainder. All I care about is the quotient. The quotient is the slant asymptote. So the first 2 terms here, since I've divided a second degree polynomial by a first degree polynomial, my quotient is a first degree polynomial. So it is 2x minus 1. Don't care about the remainder. And I set that equal to y. So the slant asymptote for this function is y equals 2x minus 1. It's a line whose slope is 2. Okay. And if you graph it, it looks like this. So again, a slant asymptote is a value that your function approaches as x increases without bound. So as x increases without bound, the value of my y approaches whatever the value of this line is. Okay, we're not going to do the application because of time. Okay, I got 20 minutes. I'm doing well. I know you're thinking, she's going to talk for another 20 minutes. Yes, I am. At least maybe you can go back to sleep. I don't know what you're, I mean, it's only going to be 8:45. If I were your age, I'd go back to sleep. When you're old and you wake up and you get up, then you got to stay up. But when you're young, you can go back to bed. Unless you got jobs. I mean, while I've been sitting here, my family's been texting like crazy about baby. I've gotten a dozen texts about baby. Anyway, mom is doing well. Baby's doing well. I'm not sure how dad is doing. Okay, let's talk inequalities. So we're going to solve polynomial and rational inequalities. Okay, so what's the definition of a polynomial inequality? So let's look at polynomial first. A polynomial inequality is any inequality that can be put in the form f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, and f is a polynomial function. So it's I mean, we've already solved first degree polynomial inequalities. We did that in chapter 2, where or was it chapter 1? I don't know. Where you just solve the inequality and you're just really careful that if you multiply or divide by a negative, you flip the inequality symbol around. But now we're going to use a different technique. And when we're talking about polynomial inequalities, we're going to focus on polynomials that are degree 2 or higher. Okay, so here is our procedure for solving polynomial inequalities. First of all, get the polynomial on one side of the inequality symbol and 0 on the other. Okay? Then you're going to solve the equation f of x equals 0. So you're going to take your function, set it equal to 0, solve that equation, and that gives you what is called boundary points. And these boundary points break up our number line into intervals. So you're going to draw a number line, you're going to plot these points on the number line, and then you're going to find the intervals that are formed by these boundary points. Then you're going to choose one representative number called a test value in each of these intervals. And what is true is this: if for your test value, the function is negative, it is negative for every value in that interval. If it's positive, then it's positive for every value in that interval. So you factor your polynomial, set it equal to 0, find the boundary points, break your number line up into intervals, then pick test points in each of these intervals. Evaluate the function at that test point. Note its sign. Is it positive or negative? If it's positive or negative for that test point in that interval, it's positive or negative for every single solitary value in that interval. Then you write the solution set, selecting the intervals or intervals that satisfy the given inequality. For example, and of course, if you have greater than or equal to or less than or equal to, you're going to use brackets instead of parentheses. Okay. Okay, so we're going to solve x squared minus x is greater than 20, which it got kind of put on the formatting on this PowerPoint slide. It's not so great. So let's rewrite it. Okay, so the first thing you do to solve a polynomial inequality is get it in the form where you have the polynomial on one side of the inequality and 0 on the other. So we're going to subtract 20 from both sides. So we're going to move the 20 from the right-hand side of the inequality to the left-hand side by subtracting it. Okay, so what this says is, looking at this, it says my function x squared minus x minus 20 is greater than 0. So that means you have to plug in x's for this polynomial such that the value of that polynomial is a positive number. Greater than 0 means positive. So when we plug in our test values, we're interested in, is the value of my function positive or negative? And where it's positive, that's my solution. So x squared minus x minus 20 greater than 0 means x squared minus x minus 20 has to be positive, has to be greater than 0. Okay, now we solve the equation. We're going to set this x squared minus x minus 20 equal to 0. That's going to give us our boundary points. And that is factorable. I highly encourage you to factor it if you can, because it's too much work to use a quadratic formula. So is that factored correctly? Yes, it is. So we're going to set each one of those factors equal to 0. So 5 is a boundary point and -4 is a boundary point. Okay. So now I'm going to go draw my number line and I'm going to determine the intervals over which I need to test this polynomial. Okay, so I'm going to draw my number line. And I had 2 boundary points, didn't I? 5 and -4. So -4 and 5. So I'm going to draw a vertical line so that I can see the intervals. So these two numbers break my number line into 3 distinct intervals. The first interval is to the left of -4. And I'm using parentheses because my original polynomial inequality was greater than, not greater than or equal to. So we're going to use parentheses instead of brackets. The second interval goes from -4 to 5. And the third interval is to the right of 5, or 5 to infinity. So that's what my boundary points do. They break my number line into distinct intervals. So now I am going to pick representative test values from each interval. And you can pick any number you want as long as it's in your interval. For example, from -∞ to -4, you can pick any number that is less than -4. So -5 maybe. So let's pick a test value of -5. Okay. In the next interval, you can pick any number that you want that's between -4 and 5. Now I suggest, if you can, pick 0. That's the easiest thing to evaluate. So I'm going to pick a test value of 0 because 0 is between -4 and 5. And then in the third interval, anything that's bigger than 5. So we're going to pick 6. Okay, so now I'm going to set up a little table here where I can write the intervals and do the test and then check the sign of the result that I get when I plug in my test value. So I'm going to set myself up a little table. My intervals were from -∞ to -4. I got that interval from that one boundary point, -4, -4 to 5, and from 5 to infinity. Okay, and my test values that I'm going to choose to test. In that first interval, I'm going to test -5. In the second interval, I'm going to test 0. And the third, I'm going to test 6. And then I'm going to evaluate my function at these values. Okay, so f of -5, plug that in, and I get 10. Well, that's positive. Okay, and then I'm going to test 0. If I plug 0 into this function, I'm going to get -20. Well, that's negative. If I plug 6 into this function, I get 10. Well, that's positive. So my conclusion is that for that test value of -5, then over the entire interval from -∞ to -4, my function's positive. So my function is greater than 0. Okay, in that second interval for my test value 0, I got a negative. So for every test value, every number between -4 and 5, the function's negative. So it's less than 0. And if we look at the last interval from 5 to infinity, for 6, the function's value is positive. So for every function value greater than 5, for every number greater than 5, this function's positive. So it's greater than 0. So my original function was x² minus x minus 20 is greater than 0. So where is this function positive? Where is it greater than 0? Well, it's greater than 0 for any number less than -4 or any number greater than 5. So the way we write this is we say the solution is from -∞ to -4, it was positive. And from 5 to infinity, it was positive. So the solution is the union of the two sets from negative infinity to -4 or 5 to infinity. Okay, and that is where we're going to quit, because the next problem, we're going to start talking about rational inequalities. Are there any questions? Well, if there are not any questions, then I'm going to let you go and let you get back to your fall break. Thank you so much for coming to class today. I really appreciate it. Have a great rest of your day, and I'll see you on Wednesday.